Good morning, girls. All right, so today these are the last notes for chapter 2. So this is chapter 2, section 6. Just a reminder, I'll get these posted tonight and you'll have like a day to look over them. Thursday and Monday are just a work day because this section, it's kind of long, just like the last section. And then Tuesday we'll have a review, and then Wednesday you guys are looking at a test. So that's kind of what the schedule is for next week. But here are the notes for chapter 2, section 6. Okay, so the first thing we're talking about today are limits at infinity. And the nice thing is anytime you're like having a limit and it's approaching either positive or negative infinity, it's gonna behave the same way, okay? So even if it says positive infinity or negative infinity, we can follow these 3 rules. So the first one is, so this is handy when we're looking at rational functions. So we'll get farther along in the notes today, and we won't always be looking at rational functions, but if you have a rational function, so you have an equation in your numerator and an equation in your denominator, and you're trying to find the limit at either positive or negative infinity, you can follow these rules. So the first one, it says, when the degree of the numerator is less than the degree of the denominator, the limit is going to be 0. The second one is when the degrees of the numerator and the denominator are the same, they're equal. The limit is going to be the ratio of the coefficients of the highest powered terms. Okay, so for that one, so if they're both something to the third, they're both cubes. So in your numerator and in your denominator, so if I have x to the third plus 7x plus 1 over 4x to the third plus 2x squared plus 8. Something like that. It doesn't matter what the equation is. But so what you're doing is you're just comparing the highest degree in your numerator and the highest degree in your denominator. So when they're the same, so like in this example, when they're both cubes, we just compare our leading coefficients. So I know that I have 1x cubed. So I would just have 1x cubed over 4x cubed. So my leading coefficients, it would just be 1/4. So my limit as x approaches positive or negative infinity of this f of x equation would be 1/4. Okay, so anytime they're the same, so you have the same power, all you do is compare your leading coefficients and then you write that as a fraction, and that would be your limit for positive or negative infinity. Okay, so they're not different, positive and negative, they're just the same. And then the last one, it says when the degree of the numerator is greater than the degree of the denominator, the limit does not exist. Okay, this one gets a little tricky because our limits don't exist at infinity, but we'll get into that a little bit more later. But typically, even if they don't exist, we're still gonna write a value there, okay? So this last one is a little bit hard, but yeah, so it says if the degree of the numerator is greater, so if this was x to the 5th, well, my degree of my numerator is bigger than my degree of my denominator, so I would say my limit doesn't exist. But then I would from there then look at my graphing calculator and look at it, and it's always gonna either approach positive or negative infinity, and then I would write that as my value. Okay, so even when it doesn't exist, because infinity doesn't actually exist because you can't actually touch infinity, so you can't limit to infinity. So even though it doesn't exist, we still write either infinity or negative infinity, okay? So follows these 3 rules, but the last rule is just kind of a little hazy. Okay, so let's go ahead, let's find some limits. So it says, let's find the limit as x approaches infinity of 1 over x. So I know that my graph of 1 over x, this is just my parent rational function. So it's gonna look like this right here. So if I look when my x is approaching infinity, so as my x is coming out here, as it's approaching infinity, I can see that I'm getting limited, it's getting closer and closer to 0. So my limit would be 0, because that's the number that I'm approaching. It's limiting, it's getting closer and closer to 0. And if I think about my rules that I just talked about, My numerator degree, so this one doesn't even have an x, so it's like x to the 0, I don't have an x, is less than my denominator degree because this is x to the first. So if my numerator degree is less than my denominator degree, I know it's going to equal 0. That was the first rule on that page. Okay, so my numerator degree, because it's x to the 0, is less than x to the first, so it's going to be 0. And graphically, I can see that that's true, and by following my rules, I can see it's true as well. Okay, then the next one, I have the same function, but this time I'm using negative infinity. So my limit as x approaches negative infinity of 1 over x. Well, if I look at this, so as I'm coming out to negative infinity, my graph is still approaching 0. It's just coming from below, but it's coming up and it's approaching 0. So I would say my limit is at 0, which follows the same rule as what we talked about. So the numerator is less than my denominator, so it's going to be 0. Okay, so those rules work for positive infinity or negative infinity, okay? So, but they only work when you're approaching infinity or negative infinity, not a number here. Okay, so don't get confused with all the limits that we've talked about in the previous sections when we were approaching a number. When we approach a number, it doesn't follow those rules. When we approach infinity or negative infinity, it does follow the rules, okay? Okay, so then limit laws, we've talked about these before, but this is basically when you can break down an equation into separate limits. And all of that applied with our limit laws that applied with the numbers as x approached a number also applies when x approaches positive or negative infinity. So in this first example, it says find my limit as x approaches infinity of 5 plus 1 over x. So my limit as x approaches positive infinity as 5 plus 1 over x. Okay, so what I can do is I can break this down into two separate limits. So the limit laws are just addition, subtraction, multiplication, division. So you can take any equation and break it down into two separate pieces and take the limit of each of those pieces and then do the corresponding, whether you need to add or subtract or multiply or divide or whatever it says. So what I can do is I can take my limit as x approaches infinity of 5 plus my limit as x approaches infinity of 1 over x. Well, we just said that the limit as x approaches infinity of 1 over x is 0, which here's our graph up here still, so our limit for this part is 0. And then if I were to think about my limit as x approaches infinity of 5, well, if I have a graph of just 5, I know that that's going to be just a horizontal line up here at 5. So here's my horizontal line up at 5. As it's going out to infinity, the limit would just be at 5 because it's just a straight line at 5. It's always approaching 5. It's always being limited to 5. So my limit as x approaches infinity of 5 would just be 5. So I would then have 5 plus 0, which is going to give me 5. So my answer for that one would be 5. Okay, so you can always split things apart to make them more simple using the limit laws, and then take the limit of each piece separately and then add or subtract or whatever you need to do with them. Okay, so the second example, this one is the limit as x approaches negative infinity. And we don't calculate any differently when we're approaching negative infinity versus positive infinity. So limit as x approaches negative infinity of pi square root of 3 over x squared. Okay, so let's go ahead and split this up so it's a little more simple. So I have my limit as x approaches negative infinity of pi square root of 3 over 1. then I can multiply by my limit as x approaches negative infinity of 1 over x squared. But instead of 1 over x squared, we know that 1 over x is 0. So let's break this into 1 over x. And then also we'd have another 1 over x. Okay, so if I break this into 3 separate pieces, I have my numerator, so my pi square root of 3. And then my denominator, the x squared, I broke into 1 over x times 1 over x. And so 1 over x is like a basic, that's like our parent rational function. So because we know the limit there is 0, it's always handy to try to break things down into that one, okay? It's just nice because we know what its limit is, so if we can break it down into that, we can just plug it in. So we know the limit here is 0 times this one, the pi square root of 3, that's just a number. So it would just be, again, a horizontal line. So I would have some horizontal line at pi times the square root of 3. So as I'm approaching infinity, or negative infinity, so as I'm coming out to negative infinity, my limit is just going to be pi square root of 3. So I would have pi square root of 3. So now if I take pi square root of 3 times 0, I'm just going to end up with 0. Okay, so my answer for this one is going to be 0. Okay? Or I can also think about it like the rational function, like the 3 rules that we talked about it. So if I look up here, I don't have any x's, so it'd be like x to the 0. So my numerator degree of x to the 0 is going to be less than my denominator degree of x squared. So it's going to equal 0 because that was the rule. Okay, so my numerator degree is less than my denominator degree. Okay, so if you see a rational function, you can just use the rules, but we can also solve it out just like we did right here, just by breaking it apart and then finding the limit of each part. Okay? Okay, so let's go ahead, let's do a couple other ones. So the first one, it says find my limit as x approaches positive infinity of 5x squared plus 8x minus 3 over 3x squared plus 2. Okay, so then looking at this, I know I have a rational function because I have a function in my numerator and a function in my denominator. So when I see something like that, I know I can use my rules. And so now I want to look at my exponents, my highest exponents. And for this, I have a squared in my numerator and a squared in my denominator. So my numerator degree is equal to my denominator degree. And so when that happens, I now look at my leading coefficients and I'm going to compare those. And so I would just put the numerator one over the denominator one. So I would end up with just 5/3. Okay, so since the degrees were the same, we then look at our leading coefficients, and then your answer for your limit is just going to be the numerator coefficient over the denominator coefficient. So we end up with 5/3 on this one. Okay, let's do the second one. So for this equation, I have the limit as x approaches negative infinity of 2x cubed minus 1 over 11x plus 2. So I have a function in my numerator and a function in my denominator, so I can use my rules. So if I look at this one, my numerator degree is going to be 3, and then my denominator degree is just 1 because I have a cubed and then just an x. So my numerator degree is greater than my denominator one, So in this case, my limit does not exist, okay? So when my numerator is greater than my denominator, when those degrees, the numerator degree is greater than the denominator degree, the limit does not exist, okay? And we'll get into like all the stipulations on that in just a second, okay? But for now, we're just gonna say that one does not exist. All right, so horizontal asymptotes. So we know what those are. Those are just gonna be, when I have a graph, anytime my graph is being limited or it's approaching some horizontal line. So if I have, say I have like a dotted line like this, if I have a function like this, maybe I also have this right here. These are both approaching this value. So this horizontal line, that's going to be a horizontal asymptote. So like by definition, it just says it's the limit as x approaches positive infinity of some function. So as I'm coming out to positive infinity, I'm approaching some b value, so just some value. So both of these lines are approaching as I'm going out to positive infinity, they're approaching that value. Okay, so that'd be your horizontal asymptote. And then same thing with the negative. If I was going out to negative infinity, if I was approaching some value, that would be a horizontal asymptote. Okay, so then it says graphs can have 0, 1, or 2 horizontal asymptotes, depending on whether the function has limits as x approaches positive infinity and as x approaches negative infinity. Okay, so we can have 0, 1, or 2 of the horizontal asymptotes. So then looking at this equation that we used on the last slide, we found that our limit was at 5/3. Well, here's the graph of it. So we can see in this graph that here's our graph, this blue line right here, and then the red line is going to be my line of 5/3. Well, I can see that my graph approaches the line 5/3 both from the top and from the bottom. So both directions, I'm approaching this horizontal asymptote of 5/3. Okay? So in that one, I would just have one horizontal asymptote in that case, because both sides, both the positive and the negative infinity, are both approaching the same line, because this one is coming down and it's approaching 5/3 from the top, and then from here, I'm approaching the 5/3 from the bottom, but both the positive and the negative infinity are both approaching 5/3, okay? But that doesn't mean that both sides of the graph will always approach the same number. Like I said, we could have 2 horizontal asymptotes, and one side of the graph could approach one thing, and then the other end of the graph could approach something else, okay? And then we would have 2 horizontal asymptotes. Okay, so horizontal asymptotes, the way we find these, so this is like literally exactly like what we do with limits. It's like the same exact 3 rules, but just like a little review. So it says horizontal asymptotes, so we're just gonna compare our degrees. So if our degree of our numerator is less than the degree of the denominator, we're gonna have y equals 0. So just like how we would find the limit was 0, well, the limit is also gonna be the horizontal asymptote in some cases as you're approaching positive and negative infinity. So whatever you're limiting to is also your horizontal asymptote. Okay, so these are like the same exact rules. Okay, if your degrees are the same, you compare the leading coefficients, and then it would just be the numerator coefficient over the denominator coefficient, and that's going to be the number of your horizontal asymptote or your limit. And then if the degree of the numerator is greater than the degree of the denominator, the graph does not have a horizontal asymptote. Okay, so that's the only one that's a little bit different. How we said the limit did not exist, well then there's no horizontal asymptote in that third case right there. Okay? All right, so let's go ahead and let's find our horizontal asymptotes of this graph. So I did already put the picture up there, so I'm sure you can see it graphically, but let's talk about this one algebraically. Okay, so I have the function, I have f of x equal to x cubed minus 2 over the absolute value of x cubed plus 1. Okay, so we can go ahead and figure out what's going to be happening on both ends. So as we're approaching negative infinity and positive infinity. So let's break it into the two separate ends. So I would have the limit as x approaches positive infinity of x cubed minus 2 over the absolute value of x cubed plus 1. And then my limit as x approaches negative infinity of x cubed minus 2 over the absolute value of x cubed plus 1. Okay, so now talking about this right here, so if I'm going out to positive infinity, we know that I'm going to plug a positive value in here, so it will be like positive. Okay, so if you think all the way back to solving absolute values, when we solve absolute value, we solve it once. We just like drop our parentheses or drop our absolute value signs and keep it positive. But the other time that we solve it, we drop the absolute value signs and we make what's in them negative. So when I'm going to be plugging in a negative right here, I would have two different cases. So one, when I have positive x cubed, and then one, when I have negative x cubed. Okay, so because with the solving of absolute values, you solve it once, where you just drop your absolute value signs and you leave it as is, so we have x cubed. And then the other time, you drop your absolute value signs and you make what was in the absolute value signs negative, so we'd have negative x cubed. Okay, so then once we have these two set up, we can go ahead and just use our rules, because these are rational functions. So I have a cubed over a cubed. So because those are the same exponent, so they're both to the third, I can go ahead and compare my leading coefficients. So I would have 1 over 1, which is just going to give me a positive 1. And then down here, I also have a cube over a cube. So then when I go to compare my leading coefficients, I have 1 over negative 1, which would give me negative 1. Okay, so then my graph, so when I'm going out to positive infinity, so as my x is approaching positive infinity, I'm also going to approach the number 1. And then as my x is going out to negative infinity, I'm going to, my horizontal asymptote, or I'm going to be limiting to negative 1, which we can see that in the graph right here. So as I'm coming out to positive infinity, the graph is coming up and it's approaching 1. The horizontal asymptote is at 1. And then over here, it's approaching the negative 1. Okay, so for that one, graphically, we can see what's going on. Algebraically, it makes sense. And this one would be an example with the two different horizontal asymptotes, okay? But you won't ever have more than two, just because you only have two ends to the graph, like one at positive infinity and one at negative infinity. So because there's only two ends, each end can do something different, but so you can't have more than two, okay? So either 0, 1, or 2. Okay, let's go ahead, let's find some more limits as x is approaching infinity. So this one, I have the sine of 1 over x. Okay, so what I can think about for this one is I can think about the composition of functions, like one function inside of another function. So this 1 over x is inside of my sine. So basically, if I think about that f of g, g of f stuff, like this function was in, like I could replace it with x. If I had sine of x and then the 1 over x, I plug in for the x right there and I would get this function. So because it's a function inside of a function, I can go ahead and separate those. So I can pull out my sine, and then I can just take my limit as x approaches infinity of 1 over x. Okay, so I just pulled this one out and I'm going to deal with the inside one first, and then I'm going to figure out the outside one. So we know the limit as x approaches infinity of 1 over x is 0. So I would then have the sine of 0. So then if I looked at my unit circle, my sign at 0 is just going to be 0. So the answer for this one would be 0. Or I could always type it in my graphing calculator, look at it graphically, and I would also see that as my x is going out to infinity, it's being limited to 0. It's approaching 0, okay? So you can look at them graphically, or you can do it algebraically. Either way, it doesn't matter. Okay, let's go ahead, let's do the second one. So this one, I have my limit as x approaches infinity of 2 plus sine of x over x. All right, let's go ahead, let's break some things up. So I have the limit as x approaches infinity of 2 plus the limit as x approaches infinity of sine of x times my limit as x approaches infinity of 1 over x. Okay, so I just broke this up. I put the 2 all by itself, and then the sine of x over x I broke into just sine of x. We could say over 1 if we want, and then 1 over x. Okay, so I know my limit at 1 over x is going to be 0. I know my limit as x approaches infinity of just 2 would just be 2. Because remember, if I think about this, if I were to graph 2, it would just be a horizontal line at 2. And as I keep going out to infinity, as it keeps going, I'm still just approaching 2. So anytime you have just a number, it's always going to be just that number. Your limit would also be that number. Okay, so I'd have 2 plus this stuff in here, the sine of x over 1, because it's multiplied by 0, it doesn't even matter what that is. I could type that in my graphing calculator, look at that one, because I wouldn't know how to solve this one without graphing it. But I know right away, no matter what it is, so even whatever it is, so whatever the limit is, it's anything. Well, anything times 0 is always going to be 0. So I don't even need to actually figure out what this is. Because I know that this one's 0, well, 0 times anything is going to be 0. So I would have 2 plus 0, which gives me 2. So my limit for this equation would be at 2. And if I typed that whole thing in graphically, I would see as I'm going out to infinity, I'm going to be approaching a horizontal asymptote of 2. Okay. Let's go ahead, let's do this last one. Okay, sorry, this one's gonna take me a lot of room, so I'm gonna erase all of this. If you wanna pause the video and write all this down, go for it. Okay, so this next one, we have the limit as x approaches infinity of x minus the square root of x squared plus 16. Okay, so when I try to figure this out, we can go ahead and split it into 2 separate limits, okay? Because I have 2 separate things. So I'd have my limit as x approaches infinity of x minus my limit as x approaches infinity of the square root of x squared plus 16. Now let's go ahead, let's think about these graphically. So the graph of x is just going to be this right here. So my limit, so as I'm going out to infinity, my y value, so my limit is also going up to infinity, okay? So as my x keeps coming out, my y keeps going up because this line's going to keep going forever. So my limit here would be at infinity. My y value, so remember your limits are always your y values. So as my x is going out to infinity, my y is going up to infinity as well. So I'd have infinity as my limit. Okay, so we have infinity minus, now this one, if we graph this one, I have the square root of x squared plus 16 So this graph is gonna look just like this. Okay, so then once I have that, I can see, so as my x is going out to infinity, my y is gonna keep going up to infinity. So I would have infinity. Okay, so then infinity minus infinity, you would think that that would be 0, like infinity minus infinity, but because infinity is just like an arbitrary concept, it's not a real number, we can't subtract infinity from infinity. So we can't say that my limit is at 0. This right here didn't actually help us. We can't solve it this way, okay? So even though we have infinity minus infinity, you would think it'd be 0, but because infinity is kind of a weird concept, we can't do it like that. Okay, so instead, let's go ahead and let's try some of our different ways we solved for limits before. So remember, we used to try to plug in. Well, you can't ever plug in infinity for x. That's not gonna work. You could also try to factor it. Well, factoring's not gonna work. We don't have anything to factor. So then the last one was we tried to multiply by our complex conjugates. So let's go ahead and do that, okay? So, yes, Carter? You gotta go to choir, right?
I have a chorus, so.
Yeah, yep, you're good. You can get off and go to choir, and then just.
Questions left. I can't hear you.
Oh yeah,